was not recording, and I'll stop sharing to make sure that we are recording the lecture, and I'll post it for you. We are recording. Okay, so we go back to the sharing here. These were the recordings from the last semester. They are not suitable for our course this semester, obviously, since they were 1-hour lectures. So this will basically disappear and will be replaced if we are successful in storing and the lectures for this semester. There will be a first midterm during the class period, a second midterm, and a final exam. So this is a regular type of a course. Each one of those tests would qualify for 20% of the grade, and the assignments will qualify for 40% of the grade. We have a calendar here for the semester. Obviously, we have no class on Independence Day, but I will assign a date for the first midterm and the second midterm. The campus wants us to have the final on August 4th. So we start today, June 12th, and we end up the course on August 4th. You'll find that I list for you here some of the book chapters that you can access, but most importantly, we have a complete set of lecture notes for what we are going to cover this semester. Whenever a chapter is assigned that new sign, like today, the preface that I am going to be covering, then you are responsible for it for the test, including the final. I will not be able to cover all the chapters here. Some have links, some do not have links, unfortunately, because I'm still working on reprogramming them from the HTML perspective with the problem with Microsoft switching different kinds of software. I have to reprogram some of the chapters right there. You could see that we have different parts. One is historically describing the dawn of the nuclear age. One covers modern nuclear science. Then we deal with the 4 forces of nature. As you know, at the Big Bang, the suggestion that those 4 forces of nature are all conjoined and they separated. So we have the weak force, which comprises radioactive processes. We have the strong force, which comprises fission and fusion systems. We have the electromagnetic force, and we'll spend some time on the electromagnetic force, but only from the perspective of gamma radiation and high energy X-rays. We leave the rest of the electromagnetic spectrum to courses in, say, electrical engineering, and the force of nature, we leave it to other classes. So we cover 3 of the 4 forces of nature. And imagine yourself as a future engineer not knowing about those 3 forces of nature. We'll try to learn about how nuclear reactors are designed and made to be operational. This is the secret of the nuclear age. So you become a part of a very elite group of engineers who knows how nuclear reactors function and how they can be designed. Radiological science, of course, is part of the weak force that we will describe, the ionizing radiation. I also cover a chapter on non-ionizing radiation. That's unique because there is evidence that the use of microwaves, like for instance in phones and in our computers, can affect our health if it is not used appropriately. Nuclear applications are listed here on the process of hydrogenation, decarbonization, the use of fuel cells in a future transportation system. And if we have time, we'll cover a chapter on the issue of global variation and how it relates to energy use in general. So whenever we cover a chapter, we are going to have that new sign added to it. Some of the links that are not working right here, for instance, will be fixed all along over the summer as I have time to do it. You could see that most of the links here that we need are already functioning. The first chapter is a preface. We are going to have here together a broad look at the energy in general, and then we'll go and detail it in each one of the chapters. If you have questions, you have the chat room available to you. Alvaro, our co-host or TA, will be able to answer you at the end of the lecture. I'll devote time for also for answering questions in that case. So here is our first chapter, and it is useful to access the wisdom of some of our great brains, like Leo Tolstoy. Nothing can make our life or the lives of other people more beautiful than perpetual kindness. So we're going to be kind to each other here. Basically, I'll read the last one. There is only one thing in life worse than being talked about, and that is not being talked about. That's from Oscar Wilde. What we can talk about as an introduction to our course here is how the United States committed itself after the unfortunate use of nuclear weapons against Japan at the end of the Second World War, in a speech given by one of the great American presidents, that is Dwight J. Eisenhower. He's shown here on the first page as Man of the Year for Time magazine. He delivered a speech to the United Nations. He's shown here at the United Nations delivering a speech. We are quoting what he said there, quote, to the making of these fateful decisions, the United States pledges before you, and therefore before the world, its determinations to help solve the fearful atomic dilemma, to devote its entire heart and mind to find the way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life. So that was a great speech. It is a commitment of the United States to devote the uses of nuclear energy for the peaceful application. That was commemorated by that stamp designated as Atoms for Peace. And the speech that Eisenhower gave was on December the 8th, 1953. You could see here a quote from his speech: to find the way by which the inventiveness of man shall be consecrated to his life. All right, man. So here we are, humans, man, and a cosmologist, Sir Martin Rees, describes our position in the universe. So man here, in terms of the dimensions of the universe, is between the very small part, 10 to the minus 20 centimeter, the nuclei and atoms, and quantum mechanics prevails in that case, and the huge sizes of the universe, from going to mountains to the Earth's size, to the solar system, to galaxies. You could see that we are in the middle here of the universe, in the middle of the very large 10 to the 25th centimeter, the size of galaxies, to the size of the nuclei and atoms, and even the composites of nuclei and atoms, like on the small scale. So we are there, part of the universe, but in the middle between the very small. Quantum mechanics controls the events there and the applications, and the very large, which is, of course, the interstellar, not just interplanetary, but interstellar distance. It's our fate, and basically we are living our lives through this in general. In our existence, we use energy. And another scientist, Kardashev, Russian cosmologist, came up with a scale that describes the level of different levels of civilization in terms of its use of energy. And he came up with what we call the Kardashev scale. And he suggested that there are different types of civilizations depending on the use of energy, which is our topic today. He designated a type 0 civilization, a type 1 civilization, a type 2 civilization, and a type 3 civilization. And in fact, we'll see in a moment that we haven't even reached yet on Earth the type 1 civilization. We're at the level of 0.7 here, and type 1 civilization. So what is type 1, type 2, type 3, type 4? Some cosmologists, in fact, have added even a type 5 beyond what Mr. Kardashev suggested. He suggests that we are at the level of 0.73 on his scale of using energy. And it turns out that a civilization is described as type 1 civilization if it uses all the resources that is available to it for its planet itself. A type 2 civilization uses all the energy resources available for its planetary system, planets around its star, its the sun. A type 3 civilization is a civilization that uses all the energy sources in its galaxy. Type 4 civilization would use it in its complete combination of galaxies, and some people even suggested the type 5 and the type omega in general. So what are those types? Those types, according to Kardashev, are described in terms of different classes. The type 1 is a civilization that uses 10 to the 16th power units of power, and the unit here is the watt. And here, of course, learning about energy, we need to know what is the watt. The watt is a unit of power or energy per unit time, and in the SI system of units, the Système International, it is 1 joule per second. So 10 to the 16 watts is a type 1 civilization, a civilization that has mastered or controlled all the energy resources on its own planet. Type 2 civilization obviously would be a civilization that uses much more. It goes up by 10 orders of magnitude here in terms of watt. Type 2 is 10 to the 26 watt, and that would be all the energy sources within their star system. If they have a star providing energy for their planets. Type 3 goes or jumps by another 10 orders of magnitude, 10 to the 6 watt, and that would be a civilization using the energy sources within their galaxy. And some astrophysicists have prolonged the scale that Kardashev suggested to us to type 4, 10 to the 46 watts, and type 5, that would be the energy accessible to this kind of civilization is equal to all the energy accessible in not just our cosmos, but in all other universes. Some cosmologists suggest that we don't have just our universe there, we have multiple universes. Think maybe about boiling water with lots of bubbles in the water. Each bubble in the water would be one civilization or one universe, in fact. These additions reflect both energy access as well as the amount of knowledge the civilization has access to. Another cosmologist, Carl Sagan, a famous one, considering immediate values, not considered in the original Kardashev scale, did some interpolation and extrapolated the values given for type 1 to level 3 levels. And he wrote a formula for this, and he described to us the level of civilization. He gave it the designation K for Kardashev, and that would be the log to the base 10. Remember here, log to the base 10 on your calculator is not the same as the log or the natural logarithm, the log to the base E. That's log to the base 10, because then it goes by factors of 10 of the power in watts minus 6 divided into 10. So if you go back to when Carl Sagan suggested this interesting formula here in 1973, the Earth was harnessing about 10 terawatt of power. Terawatt is 10 to the 12 units of power, or 10 to the 12 watts. So if we substitute that 10 here, log to 10 to the 10th to 12 power minus 6 divided into 10, you'll find that this is the same as a 10 as a power of 1, so that becomes 10 to the 13th. Log to the base 10 of 10 to the 13th is 13. It's a very interesting relationship here. That's why we use the log 10. You'll find that Carl Sagan's formula suggests that we are in 1973, we were at a 0.7. We haven't reached yes, the level 1 on the Kardashev scale. In 2018, the world used, of course, more than 10 terawatts, so we almost doubled it, 18.4 terawatts. 1 terawatt is 10 to the 12 watts. So in that case, oh, well, we have advanced to 0.73 on the Kardashev scale. Remember then 1 terawatt could power 10 billion homes, and each one having 100-watt light bulbs all at the same time. So in that case, civilization here and the knowledge that civilizations attain is measured in terms of its use of energy or power in general. Unfortunately for us as humans, so far, all that energy and power that we are using, it's sobering to think that it comes to us from dead animals and dead plants. And dead plants produce coal, and dead animals that have decayed in the oceans provide us with petroleum. That's basically dead animals and fossil fuels. And over 200 million years, energy from the sun, which is a nuclear form of energy, fusion energy in the solar system, has fueled the growth of these forests that turn into coal, and that plankton and animals in the ocean that turn into petroleum. So it is hoped that humanity will reach type 1 civilization in 100 to 200 years, but we are, it's sobering to think that we are really depending on dead plants and animals, and that's why we need to think more about using renewable sources, solar energy, wind power, hydroelectric, whatever, and maybe, it is inevitable for humanity to continue its technological civilization in terms of increasing the amount of energy and power that we use. We haven't reached yet the level of the type 1 civilization, and I'll urge you to find out how much we are using today in 2022 and figure out how much on the Kardashev scale as an interesting assignment. The problem is some scientists and cosmologists suggest that, well, the maintaining of our civilization is in jeopardy. And it came in by a very famous scientist, and the scientist will come back to describe his great contribution. That's Enrico Fermi in the next chapter. If you live by the area of Chicago, you have run probably into Fermi Laboratory, and Fermi Lab is named after Enrico Fermi. Enrico Fermi sat down with a bunch of his friends, and he came up with an interesting question. He suggested that if the age of the universe is 4.6 billion years ago, there should have been situations where other technological civilizations like ours would have emerged. And he asked the question that takes two different forms. Quote, if the universe is so big, where are all the aliens? And basically, this is the description of why is it that we are the only technological civilization that we know of in the known universe. Some people suggest that the description was in a different terms. Don't you ever wonder where everybody is? And that became known as the Fermi paradox. And that 4.6 billion years old universe. Now, remember that the universe as we know it, the farthest that we can see star from lights from stars is 13 billion years old. However, our Earth was created, as we know so far, by a supernova, where a star exploded, and that was 4.6 billion years ago. And then the Earth, solid planets like Mars and the Earth, Venus formed, and the rest of the planets are gaseous planets. Like Jupiter is primarily a gaseous planet, and if it were larger, it would start burning its hydrogen and become another sun. So again, our universe is 13.7 billion years. That is as far as we can see light from the rest of the universe with our advanced technologies of telescope that we sent up in space. So the suggestion came out that technological civilizations have filters that they have to go through. And in fact, we are going through filters right now. One of the calamities that can end our civilization is obviously nuclear war. And here the nuclear power states are threatening each other. But some natural phenomena like earthquakes, volcanic events can also end our technological civilizations. Astral assailants like comets or asteroids can hit the Earth. In fact, they ended up the 60 million years ago. They ended the age of the dinosaurs, and of course, mammals came in and replaced them. We are the mammals that replaced the dinosaurs. However, these volcanic events, astral assailants, and comets, we have no control on. We have to adapt to any new situation. But humanity also is creating its own filters. It can cause its own destruction. We mentioned nuclear war. The Spanish flu outbreak of 1918 lasted 15 months and killed about 50 million people. And then we see today that we have the COVID-19 virus that affected us. And the suspicion is that it was created as part of, as a biological weapon that escaped from a laboratory. So that, in that case, climatic change, also the release of gases like carbon dioxide and methane to the atmosphere could be man-made or self-inflicted kind of self-inflicted filters that humanity faces. So in that case, it's very important for us to learn about all what is happening around us and to call ourselves scientifically literate. This is Enrico Fermi here, who came to us with a Fermi paradox, but he was also one of the genius that humanity have generated. And in the next chapter, you could see that he was the one who built the first nuclear reactor, the Chicago Pile #1, that ever existed. The idea of the filters that can end our technological civilization is a pessimistic view that suggests, oh, well, technological civilizations generate the seeds of their own destruction. If we adopt an optimistic view, then we say that, well, there are no other civilizations, technological civilization that we can see or detect, but we are here. And we may be just too early. And the corollary to that is that we need to spread life to the rest of the universe. Hence, you'll find that humanity thinks about going back to the moon. You heard about the Artemis project by NASA. The Apollo missions sent humans to the moon. We are thinking about also getting to Mars. And so your generation may be part of our expanding life from the confines of Earth to the rest of the universe and spreading life to the rest of the universe. So here we are talking about a pessimistic view about the Fermi paradox. Some steps and hurdles to technological civilization are so improbable to pass that virtually no civilization passes it. We are going to adopt the optimistic view that we are here and that we will continue protecting it in general. All right, so let us talk about energy. How much energy is, or power to be more exact, we are using. And we'll concentrate on the United States since we are here in the United States, all of us right now. We have several sites for reactors, 59 sites. Some of them have 2 reactors. So this is the situation in the United States. And we are interested in seeing really what are the forms of energy and how much is being used. I have the latest information from the Los Alamos National Laboratory by 2021. And we compare here the different sources of energy that you are using. And another source for that diagram is the U.S. Energy Information Administration, EIA. You can get to their website and learn more and have more fun exploring it. On the left-hand side, we list here the sources of what we call primary energy. And you'll find that petroleum is our most important, really, primary source of energy. As I said, it's dead animals and plants, and we have to worry more about its depletion. As I said, 200 million years of energy from our sun, solar radiation, being used within 200 years of our industrial civilization. Natural gas follows in terms of the size, and the source in percentage is 36% of the energy that we use in the world today is based on petroleum. 32% is based on natural gas. We are still at the beginning of using renewables, even though it is part of our future, and humanity is aware that we need to replace the other sources that are depletable, like coal, for instance, which is 11% by renewable energy, and nuclear energy, which is only 8% of the total energy, primary energy that we use. Now, those forms of energy are suitable for different applications. You notice here that if you think about nuclear energy, it goes primarily for electrical energy production. If you talk about electricity retail sale and the power sector, some very small amount, 1% only, comes for petroleum. Petroleum, as you could see from that diagram, that's called the Sankey diagram, as it's called, is primarily used for a transportation system. That is the end use. So here you start with 35.1 units of energy. In that case, that's energy, not power, but energy. Remember, Kardashev uses power. Here we're using energy. And the energy in that case unit is the British thermal units. That's BTU. So 35.1 BTU of quadrillion BTU, and the quadrillion unit is takes the first letter and calls it the Q. So the Q is a quadrillion British thermal unit. You could see if you add 35, 31, and 12, and 10, and 8, you end up with about 100 quadrillion BTU of energy is the primary source used in 2021. Now, these sources of energy produce electricity, and electricity goes into other uses. This would be the primary sources. This would be the secondary sources. You notice that petroleum is primarily for producing industrial products, 25.9 Qs, and transportation. Electricity is not used. Petroleum is not used much in producing electricity. Electricity is primarily produced by natural gas, renewable, coal, and nuclear. The end-use sector in terms of energy produced is 37% transportation uses, 35% industrial, almost equal to each other. Residential uses 16% and 12% in commercial uses. Okay, wonderful. So here we start with 97 quadrillion BTU, but then we end up with uses of those in other end-use products at 73.5 quadrillion BTU. So it tells us that there are losses in the system here. Some part of the primary energy is lost. And if we look at the efficiency in terms of electrical production only, you'll find that we only have an efficiency in our energy system of 37%. This is another form of what is called the, from the Lawrence Livermore National Laboratory, what we call the Sankey diagram. And basically, those Sankey diagrams are a type of flow diagram in which the width of the arrows is proportional to the amount of energy used. So we lose part of our energy. In fact, you could see 67% of the energy that is primary available to us: solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. We only get energy services of 32.7. And the total amount here in the Sankey diagram is 100.2 quads. The unit of the quad is the quadrillion BTU, or British thermal unit. So if you take 32.7 divided into 100, this is the net energy produced. I'm asking you to simply calculate it, to figure it out from the from the diagram. The efficiency of energy, our energy system, is 33% only, of 1/3. 2/3 of the energy that is available to us is basically rejected energy to the environment. So the first important aspect of energy production is to increase that efficiency, both in the residential, commercial, industrial, and transportation uses of energy. And then also not just our goal should be the increasing the efficiency of the uses, but also think about the sources of energy. As I said, coal, natural gas, and petroleum are depletable sources. They're not going to be there in our future. So our emphasis should be on solar, hydro, wind, renewables, and a future where nuclear should be part of our future. Notice that nuclear, solar, hydroelectric, wind, and even some natural gas are really primarily dedicated to produce electricity that is fed into the residential, commercial, and industrial uses. Petroleum, in fact, is primarily used in the transportation system and some of it in the industrial system. But we still have a very low efficiency. And in that case, we need to increase the efficiency and have an optimized system of energy sources. This is the plan or estimate, again, from the Lawrence Livermore Lab of our use of energy by 2025. And you notice that the 100 quadrillion or quads per year would be increased by 1/3. I suggest it would be 133 quads of energy to be used. Again, the rejected part would be 73 quads. The useful energy would be 59 quads. But notice that definitely there is now a larger emphasis on the nuclear. We need to increase the use of nuclear. You will be part of that future as you learn about nuclear energy, and definitely the renewables, the hydroelectric, wind, and solar. And solar, in fact, wind at some point was increasing in terms of capacity by 29% per year. And the one that is increasing with the largest percentage right now is solar. Solar is even ahead of wind in terms of the renewables. In the whole world, nuclear is taking also a very important aspect, but in the United States, we are stagnant. We haven't been increasing our capacity in terms of nuclear energy production. So Sankey diagram is very important, and you could see that it's inexorably a fact that our use of primary energy in these quadrillion British thermal units, the quad units, has been increasing. And if you look at coal here, you'll see that coal is decreasing. Coal power plants are being retired because we know that they are a source of pollution. Natural gas seems to be increasing. Crude oil also increasing. Nuclear is staying the same, and renewables are taking a major part in providing our energy source. So the future is renewables plus nuclear, without really saying that we are not going to use coal. We'll use it, but to a lesser extent that we have today, and that is the vision of our future. Now, as people suggest that you heard about the concept of peak oil. Peak oil refers to conventional oil. Now, of course, we have methods of increasing oil production. Oil in the ground is not like a lake, free water. It's more like water in the sand on a beach. So we are able to extract at most 1/3 of the oil that's available in the ground. So what do we do? Well, we use secondary methods of production like fracking, hydraulic fracturing. And in fact, the Exxon company was telling us just yesterday that they have new methodologies in that fracking. But the discovery of oil fields like the Ghawar oil field in Saudi Arabia, this is what's called an elephant oil field, has gone up around the 1960s, as you could see. Some came Alaska in the 1980s, but the discoveries of conventional oil is decreasing. And for the future discoveries, it's decreasing even more, whereas the consumption in billion barrels of oil per year, the unit is GB per A. A stands for annum in Latin, which means per year. It has increased and came down with the financial crisis, and then, oh, it's going up back again. And we are using really a resource that is not being replaced. So that's why we cannot depend totally on oil. Some people suggest that conventional oil has reached its peak in the 1970s here, and there is a time lag in terms of the lower production. So for the continuation of our industrial or technological civilization, we cannot continue depending on the fossil fuels source. We need to switch to the renewables combination with nuclear energy. Some people argue about this idea of peak oil, as it's called, and the argument goes on. Some people say, oh, well, new technologies will be able to extract more of that oil that's available in the ground. But the facts are that some countries, in fact, have already reached the peak oil. This is the total oil production in the UK. You could see they reach a peak here in 1980s. In the 2000, they reach another peak from the North Sea, and it's coming down. Denmark, the Netherlands, and Norway also have had huge resources in the North Sea. It's definitely, they have reached peak oil here. They cannot find more fossil fuel. As production decreases, you could see that the price increases. And at some point, if the energy that you expend in producing the oil, pumping it, refining it, sending it to the consumption center, exceeds the energy that we get out of it, then it becomes uneconomic, and you cannot end up using it. So replacing the oil with a combination of renewables and nuclear is the future of energy production and the future of humanity in fact. This is the history of oil production in the United States. It reached a peak here in the lower 48 states, that excludes Alaska, in 1970. This is what is designated as the peak conventional oil, 1970. Oil was discovered in Alaska, so the decrease in the lower 48 states was now supplemented by production from Alaska, Prudhoe Bay in Alaska. And then later, we came up with the technology of fracking or hydraulic fracturing and horizontal wells. So in that case, you there is a new peak that has been reached in 2019, and fracking has environmental issues associated with it in the depletion of fresh water supplies, and even water acts as a solvent. So supposedly it causes earthquakes. So that peak here is not going to stay there for a long time. The offshore production, as you could see, is going down. So our future depends on, again, a combination of nuclear energy and renewables in an optimized fashion. This shows us the power fluxes, and which is the energy consumption per person. If you take watts and multiply it by 1,000, that's a kilowatt. If you multiply by hour, then the watts is joule per second. Joule per second multiplied into hours becomes units of energy per day, per person, in terms of different countries in the world, against the population density of people per square meter. The source is David McKay, and he shows us here that the energy intensity really that we have so far in different countries is very low if we start depending only on energy crops. Even wind power is not enough. Solar photovoltaics, PF here, concentrated solar power. Photovoltaics, of course, is different than concentrated solar power, where you use troughs or in the form of parabolas and concentrate the energy. The only way that you can get a large amount of energy intensity here, watts per meter square, is really to go for nuclear energy. So that's why the energy scientists suggest that, oh, we should really try to get as much of the energies from the renewables, the one that have low the low energy density, and complement it with nuclear energy in our future. Now, some people suggest, oh, nuclear energy has lots of risks in terms of possible accidents and the release of radiation, and the facts deny this. In fact, if you think about the death per terawatt hour, that would be 10 to the 12 watts multiplied into hour per unit energy, you get about 30 deaths from coal. From what? Well, the particulate matter that are released in coal is a source of pollution. It gets into people's lungs and, well, kills them. And so that is death from air pollution from coal. And also you deal with a large amount of materials. You have to mine coal. So you get mine accidents, transportation accidents, railroad cars being maybe derailed, and a coal power plant of 1,000 megawatt electric of power needs 100 cars every day of coal to come and supply it, whereas a nuclear power plant needs only to be refueled every year or a year and a half. So very small amounts of energy, as you'll see, because nuclear energy has a very high energy density or a very high specific energy. The deaths from accidents is almost negligible. And there is no air pollution unless, of course, you have accidents. So we say that in nuclear energy production, safety is the paramount. But you could see that coal is not that clean source of energy. It's a very dirty source of energy. Petroleum follows it, biomass, natural gas. We are depending on it quite a bit today, but it doesn't have many deaths from accidents. But nuclear is almost really negligible unless you have accidents in that case. So what are the trends in energy uses in general in the United States? You'll find that solar energy is increasing by a very high rate, 46%. Wind energy, as I suggested, 29% between 2015 2017. Hydroelectric, 16%. Biomass, 4%. And coal is decreasing. So we are really doing the following. We are replacing coal as a primary energy source by solar, wind, and hydroelectric power. And we are moving in the right direction from that perspective. Notice again, this is based on the Sankey diagram, that petroleum use is generally used for transportation. Nuclear is primarily used for electric power generation. And that's why we need an optimized system of energy sources. You cannot use nuclear for transportation, well, unless you turn it into electric power and then use electric power, store it in batteries, and then, of course, the electric vehicles revolution that we are seeing happening in front of our own eyes. And this is a diagram that I'm showing here behind me on the screen. You'll find that most highly populated regions of the world are the ones that use the most amount of energy. In fact, we are extended our life by having a longer day with having those lights. Highest populated regions here are the United States, as you can see, Europe, some parts of the Middle East, India, Japan, and Southeast Asia, and some only a very small part of East Australia. This is a nice picture from NASA. We haven't yet done any population extension in Antarctica. And you could see here, the higher the population density, the higher the use of energy, particularly at night. This is the Mediterranean Sea, and this is the delta of the Nile. That's Egypt. You could see here that the population just is around the course of the Nile. You'll find here Jeddah in Saudi Arabia. You'll find here the area of Gaza and Palestine, Jordan. So whenever populations are large, the higher the energy that we are using. And this is another picture on how we turn the night into day with a high population density. This is the Nile Valley. This is the Mediterranean Sea. That's the area of Israel, Syria, and Jordan. One future aspect of nuclear energy use is that it can be used to turn arid regions of the world. This shows here a desert area. You can have a nuclear power plants. 2 units are shown here. You can produce thermal energy, and that thermal energy can have 2 uses. You can produce electricity and use electricity for industrial processes. So that becomes an industrial part of using nuclear energy. But you also can use the heat to desalt seawater, turning seawater into fresh water. And in that case, you can use the fresh water to plant those arid areas of the world along the seashores. And this would apply to the Western United States. It would apply to South America, and particularly the Middle East. And in that case, a future use of nuclear energy is not just to produce electricity, but to use it in the concept of an agro-industrial concept. So this is part of the vision of using nuclear energy in our future here. This is the how we are using consumption of electricity from the Energy Information Administration. Hydrocarbon constitute an amazing 81% of our energy. So we are using a depletable resource, something that is depleting with the highest possible rate. Nuclear comes to our help. It's 8.7%. Now notice that nuclear produces primarily electricity at this time. We are not using it for freshwater, producing freshwater supplies. So it provides us with 9% of our total energy in the United States. 81% is coal and carbon. We are still at the beginning of using hydroelectricity, wind, solar, and the renewables, and they have to come in to replace the hydrocarbons, which are depletable. And I do mention here depletable because that is the main concern that we must have about our energy source from fossil fuels. That plants and animals, to make it just say it in a simple way. This is the United States electricity generation by source amount and share in total in 2017, more detail of what I have shown in the previous table. In the overall picture of energy use, you find that there is a trend today in the United States to use natural gas as a primary source of energy. So natural gas as methane, as CH4, is basically the main source of electricity production. Coal is 27%, nuclear 19%. Notice the difference here in the two tables. Nuclear produces for us 8% or 9% of our total energy. However, in terms of electricity production, 20% of our electricity, according to that diagram here, 20% is nuclear. Hydroelectric, wind, biomass, solar, and geothermal take the rest. So these are the renewables here and the nuclear, and they have basically the task of replacing the coal in our future energy picture, or the fossil fuels in general. Now, some people suggest, of course, that it is necessary to avoid the use of coal because of the emissions of CO2 and methane, CH4, which are greenhouse effects, and they suggest that this is affecting our climate. This is the diagram that shows the annual temperature above and below average, starting from the 1800s. It was below average, and here now it's above average by 1.5 degrees. And we want to limit that increase, or else we'll end up changing the situation of our climate. And I think the depletion of those resources should be the main concern, more than it is just changing the climate, which of course is also important. In fact, changing the climate can become one of those filters that we suggested the Fermi paradox would advance as a way of ending a civilization by its own hands. So nuclear energy becomes part of our future. We have to admit it, and we can use it in an environmentally sound way. In fact, this is the South Texas Project Nuclear Power Plant here in Texas. These are 2 units. The plant is the 2 units, so we call it a plant, but it has 2 different reactor units. This is the containment vessels for it, but you could see it is part of a large 22,000 acres nature preserve here. So nuclear power generation and the environment can coexist. Some people who are smart enough in the Middle East, which is a source of our petroleum, have realized already that their future depends on having sources of energy other than petroleum. Whatever petroleum we still have in the ground is going to be used as we suggested, industrial uses, producing fertilizers and chemicals, as well as for transportation. So here it is, the Baraka 4-unit plant. You could see 1, 2, 3, 4-unit built in the region of Abu Dhabi in the United Arab Emirates by help from South Korea. And basically the first unit is already operating. So here is a region of the world where people who are in charge or are very smart enough to understand that petroleum is depletable. It's not going to be in their future, and nuclear energy being developed there for survival and industrial uses as well as domestic uses. Each one of those units is 1,400 megawatt electric, and mega means a million, watt, the unit of power, joule per second. This is what you use to describe the capacity factor of nuclear power plants. And the 4 units here shown, one of them already is operating. The 4 units are expected to supply 25% of the United Arab Emirates electricity demand. And whatever petroleum they're producing, they will export it. And of course, I expect a larger demand for their petroleum as it gets depleted in different parts of the world. Well, all right, so we are going to think about the use of nuclear energy. The primary use so far is not really freshwater production, even though it will come to the fore, but it's electricity. So how do we use electricity? We have to use it in a judicious way. And the vision for the future of your engineering basically community, you will be the engineers of the future, is the use of what we call the Internet of Things for electrical power generation. So what is an Internet of Things of electric power generation? It's really how in our future electrical energy is going to be produced. And you could see here that it encompasses, and in fact, some people call it the Internet of Things. So if we have the Internet, the www today, the Internet of Things is for electrical production is shown in that diagram. You could see here that renewable energy sources are going to be part of our future. There is no way around it. So the development of wind, solar, thermal, and solar photoelectric are two different forms of producing solar energy, of course, are going to be part of our future. However, they have the intermittence problem. Some people call it the capacity factor, but it's really intermittence. The sun is not available at night, and the wind doesn't blow all the time. So we'll have those sources here. And if we want to implement them as part of our energy picture, in addition to centralized base load generation, and the base load generation would be hydroelectric, coal, whatever is coal is left, geothermal power, but primarily nuclear. Nuclear power plants have the ability of operating at a very high capacity factor. So when the wind and solar are not available, the centralized power is available there. For us to use the renewable energy sources, again, because they're intermittent, we need to have backup systems like maybe gas turbine power plants running when there is no wind or no solar energy. And we need to store the energy. We need to store the energy. And the main storage medium today that we are using is, of course, the lithium-ion batteries. That's a chemical form of storage for our fleet of transportation systems. Some states like California and some countries like Denmark and Norway basically don't want to have any more ICE or internal combustion engines driven cars on their highways. They expect to have electrical vehicles in 2035, in fact, very soon. So energy storage system that we can think of is pumped storage. If you visit Lake Michigan in the summer, you find that in the hilly parts of Lake Michigan, water uses electricity available from power plants, including nuclear, to pump water up a hill. And then when it's needed, it's allowed to flow down the hill. So you turn the potential energy into kinetic energy, and you get electricity when you need it after storing it. Batteries, chemical storage, flywheels are not used very much. Hydrogen and stored reserve gas turbine and stored reserves. Hydrogen is a way of using electricity, and I'll devote a chapter to that. You use electricity to dissociate the water into hydrogen and oxygen, and then hydrogen. Now this is an electrolysis process. You can reverse the process by using the hydrogen in a new kind of engine, the fuel cell. And an interesting competition is arising now between the largest producer of vehicles in the world, Toyota. Toyota for trucks and even passenger cars are suggesting the use of hydrogen with fuel cells, whereas Tesla in the United States is using chemical batteries, chemical storage. So you could see here the picture is now will still remain with a centralized power generation that would be primarily nuclear. Wind and solar are taking, in fact, a very large part of the energy electrical picture. We are still starting to develop energy storage systems, and all of this has to be controlled by internal Internet of Things control. So many among you will be part of that future energy picture. And we cannot ignore here that at the same time that we have centralized power generation, renewable energy sources, as well as energy storage, that decentralized generation is going to be a very large part of the future. Like you see people already putting solar panels on their homes, and this would be private. and industrial consumers. You could see many businesses around Champaign-Urbana having their own wind turbine rotating, storing the energy here, probably in batteries, and using it when it is needed. So the future there for energy is very interesting. It provide all the engineering profession with jobs to do, like in the grid system where you produce the wind power, you have to transport it to the consumption center. So electrical engineers, mechanical, chemical, nuclear, everybody in the engineering profession will contribute to the Internet of Things in the future. In fact, that Internet of Things is already implemented in other countries, not in the United States though, but in France. This is the power system in France as shown here, and detailed by French electricity generation. The date, I think, was January 2020. I took that picture of their at over a 24-hour period. You could see here 0, midnight, 23, the next day, 24 hours. And they show us here the fractions of their use of electricity. This electricity here, that color is, guess what? It's 48,894 megawatt of nuclear energy. You could see how the French, since they don't have meaningful supplies of coal or fossil fuels, their dependence at 70% of their electricity. That's only electricity, by the way. Only electricity is nuclear energy. They supplement it with that other form of energy here, which is obviously hydroelectric power, 12,000 megawatt. And then they use also gas here. In French, it's really natural gas, or with another supply of natural gas. And notice here a part of the picture there that is negative. What does it mean? Negative here, this means that, oh, these are exports. When they produce more energy than they need, they export it to other countries in Europe. And here you could see that wind power is part of the picture there. And as wind power is there, like around noon, you could see that they have also some solar energy. This is a small amount of solar energy. Notice that the solar energy is really produced primarily energy around noon. The French here are exporting some of their power. Very little oil, very little coal, substantial amount of natural gas there on top, but it's primarily nuclear energy. So they really are looking at, and they have a feature in the nuclear power plants in France, is that they should be load following. Meaning what? Meaning that when the demand for electricity, say for air conditioning in the summer or for heating in the winter, the nuclear power plants follow the load. That is not the case in nuclear power plants in the United States, and it needs to be implemented in any new design. So this is a 24-hour period. You could see here how the demand of electricity changes, and all those sources contribute to the production of that electricity. Here, that's midnight. You see people are sleeping, but then comes the morning, 6 in the morning, they start going to work. The demand for electricity goes up, and it's satisfied here. In that case, the nuclear power plant is producing at almost a constant rate, but natural gas here is helping. Notice the uses for storage. They have 53 here megawatt, a little bit here being stored, and then here you could see some exports of the energy, but this is the solar energy here. The day goes on, electricity is being produced, and then comes the night, the electricity decreases back again. And we have basically all the different sources of energy, not just coal or nuclear or petroleum alone, are providing that energy, at least in the French grid. So this is a picture in the whole world. And I'm discussing here the need in the United States for nuclear power load following, which needs to be implemented in any new designs in the United States. Access to nuclear energy and hydrocarbon resources remains a privilege, unfortunately, in the whole world to the developed industrialized nations. However, the United States Nations General Assembly has ratified the Universal Declaration of Human Rights, and Article 25 states, quote, Everyone has a right to a standard of living adequate for the health and well-being of himself and his family, including food, clothing, housing, and medical care, and necessary social services, and the right to security in the event of unemployment, sickness, disability, widowhood, old age, or other lack of livelihood in circumstances beyond his control. This is a human right, and it has been recognized since 1948. Many of you were not born then, but this is the concept of human right. Electrical energy production, in that case, fights poverty and becomes a human right for all the humanity and the well-being of all the world. This is the different primary sources of energy production in the world. The emphasis today seems to be on natural gas. We are burning natural gas, well, because the supplies are ample. And you hear about Russia and the Europeans having arguments and the United States intervening in terms of the resources of natural gas that the Russians have been providing to Europe, but not anymore, or they're still providing it, in fact, but on a lower scale, and it's not being admitted. But our according to the Energy Information Administration, the dependence in the world right now is still fossil fuels. Coal has been reduced in its basic contribution. The main source of energy production in quadrillion British thermal units is on natural gas, followed by crude oil, coal. And all of these here, look at this, all of these are dead plants and animals. Fossil fuels are dead plants and animals. Nuclear is 8% of the overall energy picture. It is the destiny of humanity that nuclear and biomass, wind, hydro, and all the renewables have to be developed in replacement for the fossil fuel. So this is the vision of our future. And for nuclear energy, it's not going to be just fission as we have it today, but also fusion. Hopefully we'll develop fusion too. The French are leading the world in terms of the use of energy production for electricity. You could see here 1, 2, 3, 4 units in one of their plants, the Paluel 4-unit nuclear station in northern France. This is another plant here, Cattenom. Another, you could see 1, 2, 3, no, the fourth unit is not shown. Many people mistake those cooling tower for being the nuclear power plants themselves. That is not true. Instead of getting the cooling of the plant, and you need to reject some heat to maintain the flow process in the thermodynamic electrical steam production process, instead of cooling the coolant of the plant in a river or a lake, some water is taken from the lake or and simply used to cool the water by producing some steam. In that case, you don't cool the water supply itself. Nuclear fuel, as that's after it's being used, has to be stored for about a long period of time, 5 to 10 years, in fact, until the radioactivity cools down, and then either reprocessed, like in some countries like Japan, France, the European countries, Russia, or returned back into the ground where we mined the uranium in the first place. Uranium has a very long half-life. It has been there for billions of years and will remain there for billions of years again. So as we mine the uranium from the ground, we extract some energy from it, and then whatever is remained that is not used should be returned back to the ground. That is the plan, at least. The share of electricity from different sources in the United States has been primarily coal, but I think you could see now from the previous diagram, worldwide, it's natural gas taking over from coal, and nuclear has been almost steady at 20%. And this is the overall energy picture. You could see still our dependence is on fossil fuels. This is 95 quadrillion BTU, or one quad, 95 quad of energy. 37% of it is petroleum. natural gas 25%, coal 20%, nuclear 9%, and renewables, including solar, geothermal, wind, biofuels, wood, and hydropower, is only 8%. So that value here should be increasing as we retire coal power plants and lessen our dependence on petroleum as it becomes basically a depletable resource in our future here. This is the 2021 use of the United States in energy by energy source. You could see that renewables, well, it's only 12%, but it is taking shape. Natural gas, petroleum, coal is the one that is really being retired, which is a good direction there. Renewables are a larger field here. It could be geothermal, solar, hydroelectric, wind, biomass, biofuels, and even just burning wood has been used to produce power. The cost of electricity, as you understand, of course, depends on the different sources of energy. Because wind and solar are very diffuse sources of energy, you need a large amount of materials in the collectors, say whether it's photovoltaic or if it's thermal concentrated energy. You can reach 11 cents per kilowatt hour. Not a kilowatt is 1,000 watt a joule per second. So hour and second cancel. So that's unit of energy, the kilowatt hour. That's what you pay for your bill every month for the utility from which you buy your electricity. You don't pay for the kilowatt, the power, you pay for the energy, which is kilowatt multiplied into hour. So hydroelectric power seems to be the cheapest form of energy. Oh, wow, that's a renewable. So we should emphasize hydroelectricity, but hydroelectricity basically is a resource that is connected to the availability of water for agriculture. You don't discharge water from dams just for electricity. You discharge water from dams also for agriculture. And you have environmental concern about maybe salmon hatching from the ocean to rivers where they were born. So there is limitation on what we can use for hydroelectricity, but it's the cheapest form of energy available to us. Coal and geothermal and nuclear, as well as natural gas, are all within the same range, 6 to 7 cents per kilowatt hour. Wind and solar still needs to come to the same level as geothermal and nuclear. Wind, in fact, is coming very close to nuclear and the coal. Solar is needs more time to reach the same level. Now, here is what's called the levelized cost of electricity. Levelized cost of electricity is the cost of electricity taking into account the discount rate and the inflation rate over a 20-year period or more, or 30-year period, the period over which we are using the energy resource. And you could see here, solar thermal needs still to catch up on here. Wind is doing really fine, and that's why we learn about wind power. And you just drive around the Midwest here as a huge resource of wind power. And that's why we also have a course just devoted to wind power generation. Now, we need one that would be devoted to solar to improve and reduce the cost of electricity from solar energy. There should be neat ideas to be pursued. One aspect of why it is that nuclear and wind are so nuclear, in fact, and coal are part of the energy picture is nuclear energy has the highest capacity factor. The amount of energy that is in materials or matter is so large per unit mass that you can run a nuclear power plant at a capacity factor of 90%, meaning that it is available producing power for you 90% of the time. You need to refuel it once a year or once every year and a half for the existing designs of pressurized water reactors and boiling water reactors. Coal also has a very high capacity factor. Natural gas combined cycle. Combined cycle natural gas is when you burn using that case a gas turbine cycle, the Brayton cycle in thermodynamics. and you produce, you burn the methane or the natural gas, and then you use the gas exhaust into a steam cycle. That's why they call it the combined cycle. So it's a gas turbine cycle combined with a steam cycle. The capacity factor is 40%. Geothermal is 90%, the same as nuclear energy. So these are two base load kind of sources of energy. However, photovoltaic and thermal are only 15%. And in that case, energy storage becomes paramount for us to take advantage of the renewable sources of energy. This is locally here. We have a utility, Amaran, Illinois. It's a utility from Missouri, providing us with electricity. 48% of the electricity that we are using right now, yourself and myself, if you are in Illinois, is coal energy. 16% is nuclear, natural gas, 23%, very little wind, 7%, and other sources, 1%. The world is embarking on, of course, on the use of nuclear energy big time. You find that China have very high levels of pollution from coal, so they are switching to renewables for their future energy picture, as well as nuclear power plants. So these are, that shows here basically planned nuclear systems and the existing systems. That's China, India, the European Union, and Asian countries. So in that case, the world is embarking on an age of renewables as well as nuclear energy. This is a concentration of nuclear reactors, and you could see that their concentration is in the industrialized nations. Lots of them, about 100 in the United States, the European countries, Japan, some in India, but the rest of the world really doesn't have many nuclear power plants in operation. The number of nuclear power plants is largest in the United States, followed by France. And even though the United States produces 20% of its electricity from nuclear power plants, France produces 70% of its electricity from nuclear power generation. Japan has had a large number. They shut that down after the Fukushima earthquake and tsunami accident, and they reviewed their safety features, and they're restarting back again. They depended for some time on natural gas, but they cannot continue. The price in that case is economically unfavorable. Russia, South Korea, Germany, Canada, Ukraine, China, and Spain. This is a distribution of the nuclear power plants in the United States. Let me maximize this here. You find that our state of Illinois has a large number of plants. The nuclear power plants are also concentrated along the seashore. We have about 93 licensed plant in the United States. 62 of those reactors are a design called the PWRs. Try to remember the acronym. That's a pressurized water reactor. We'll, of course, describe how it functions, how it operates later on in a different chapter. And to a lesser extent, 31 boiling water reactors. And this is according to the United States Nuclear Regulatory Commission. This is a diagram for a pressurized water reactor. You could see that you have a core here where you have the fuel. The fission process happens. It produces steam. The steam goes to a steam generator. You produce steam. It goes to a turbine. The turbine rotates and produces electricity for us. You don't allow the water in the pressurized water reactor to boil, so you pressurize it here. These are the pumps actually, but there is a component that we call the pressurizer. And all of this is contained within a containment structure that protects the internals against direct impact from a Boeing 747 or a light pole traveling as a missile at 100 miles per hour. The boiling water reactor doesn't have a steam generator. The steam is produced in the core itself. The steam goes to the turbines and where electricity is being produce. These are the two designs that we are using in the United States. This is the operational plan, the United plants in the world. It needs to be updated, but on the average, we have 97 plants in the United States. So the United States is still the leading country in the world in terms of nuclear power plants. France follows. There were only 2 plants that have, in fact, started operation in the United States. 2 of them, 11 were on the drawing board of 19 proposed, but there is no progress, unfortunately, on the planned or proposed reactors in the United States. France is different. They have 1 under construction, 1 is planned, and 1 is proposed. Russia is a much larger number, but the real country that is embarking on a large nuclear power program, as well as renewables, in fact, is China. They have 120 proposed reactors for their industrial processes in their future. Nuclear power plants have emissions, in fact, but the emissions are very small. The Ameren, Illinois emissions of carbon dioxide, because they use primarily coal for the production of electricity, is 1,372 pounds. NOx, nitrogen oxide. These are what's called the NOxes and the SOxes. These are pollutants from the burning of coal. NO, nitrogen monoxide, and NO2, nitrogen dioxide. Here, SO and SO2. The nitrogen oxides generate nitric acid in the atmosphere. Then that is the pollution part of it. They end up in people's lungs and cause them lung diseases and kill them eventually. Sulfur dioxide combines in the air with water. It becomes sulfuric acid, also hurts the lung. Nuclear waste, as you could see here, is very, very minimal, 0.0009 pounds from the use of nuclear energy. High level would be something that you have to store in deep underground facilities. Low level could be stored close to the surface in low-level disposal sites. As a journey, the World Future Energy Summit, Jeffrey Sachs, the director of the Earth Institute at Columbia University, commented. I think I would like us to cover that comment. We are emitting 35 billion tons of CO2 this year. By 2050, in a much larger world economy, we have to be emitting less than 15 billion tons if we want to maintain the increase in the temperature of the Earth by 1.5 degrees. So the world economy is going to grow by 3 times, but we have to cut back by more than half our carbon emissions. What does that mean? It means keeping the coal under the ground. It means changing to electric vehicles. It means radically different building codes. It means facing the fact that our energy, when we produce power, has to be emitting about 100 grams of CO2 rather than 700 grams per kilowatt hour of electricity generated. That is now emitted when we produce electricity. In a way, this is straightforward arithmetic, but our political systems do not want to face straightforward arithmetic because it means making choices. It means telling the coal industry that unless you have the carbon capture and sequestration, the coal must stay underground. It means saying to the oil industry, but by 2030, our vehicle fleets must be electric powered. They cannot be internal combustion engines or ICEs if we are serious about this problem. So far, we are not serious about the problem. I pity our children, and I'm scared for them because we are not facing the honest carbon budget of the planet. Here is this, it suggests that nuclear energy is important for us because of the fact that it does not contribute to changing the climate. So think about humans and plants and animals being like fish in a fish tank, and we are polluting the fish tank, and eventually the pollution in the fish tank would kill us all, plants, animals, and humans. Some people suggest, of course, that radioactivity is contributing new elements that are toxic to the environment, and that is partially true because uranium in the ground already is radioactive, and it will remain radioactive for billions of years, not millions, billions of years. It has been there since the creation of our Earth, 4.6 billion years ago in a supernova when a star exploded and created the heavy elements, uranium and thorium, also the iron and the calcium in our bodies. The fact is that we can extract some energy of it and then put it back into the ground. It will remain radioactive anyway. Different designs like the pressurized water reactor that I mentioned earlier would have radioactivity that generates radiation, and it's measured in terms of the dose. That is sievert, the unit of dose equivalent per gigawatt thermal, billion of watt thermal year. And you notice that it takes a long time for the design of the PWR for the radiation to decrease. But if you use thorium-based reactors, that is part of our future, hopefully, then you can reduce the fission production by 3 orders of magnitude in our future. The expected global demand and shortfall in terms of uranium-based case demand is very large, and the different sources of uranium, as you could see, are not able to satisfy the demand. So here are secondary supplies, and Kazakhstan is a country that has lots of resources in uranium, as well as Canada. So all over the world, uranium would be in great demand, and we can extract it, in fact, interestingly enough, from the oceans. Oceans contain lots of uranium. One interesting aspect of nuclear power generation is that it's environmentally kind of benign. This is a picture here in the summer, and this is a picture in the winter of wind turbines here on the prairies. This one is rotating, obviously it's producing power in the winter. These are also rotating. And in the background here and here is a nuclear power plant. And this nuclear power plant basically is 2 units. There are 2,000 megawatt electric boiling water reactor, the LaSalle plant. Our class here, the 402, when we didn't have the COVID-19, we went and visited both the nuclear power plant and the wind farm. The existence of the wind of the nuclear power plant is beneficial to the use of wind energy. Why? The nuclear power plant in that case is connected to the grid, and if you produce power, the concept of dispatchability from wind power, you need to sell it, so you have to put it into the grid. So in that case, the combination of nuclear and wind becomes a very useful kind of combination, and it does not affect really the production, agricultural production. You could see here in the summer, the rows of cones really right around the wind turbines and the nuclear power plants. And another very interesting aspect of it is that both the nuclear power plants and the wind turbines were built by the General Electric companies. Those wind turbines are 1.5 megawatt. That is the rated power wind turbines, and they're 80 meters in height. And the boiling water reactors and the wind turbines are manufactured by the same company, the General Electric company. So in that case, they complement the renewable in that case, and the nuclear complement each other. Electricity is going to be part of our future, in particularly plug-in electrical vehicles. And as the number of electrical vehicles increases, they become a form of energy storage. So the whole fleet of electrical vehicles that we are developing would become a way of storing the energy. So you charge them at night from electricity produced from nuclear power plants, maybe within the concept of the Internet of Things in general. Patrick Moore, the co-founder of Greenpeace, wrote in 2006 in the Washington Post newspaper another quote: In the early 1970s, when I helped found Greenpeace, I believed that nuclear energy was synonymous with nuclear holocaust, as did most of my compatriots. 30 years on, my views have changed, and the rest of the environmental movement needs to update its views too, because nuclear energy may just be the energy source that can save our planet from another possible disaster, catastrophic climate change. Look at it this way: more than 600 coal-fired electric plants in the United States produce 36% of the United States emissions, pollutants in that case, or nearly 10% of global emissions of CO2. The primary greenhouse gas responsible for climatic change, that's CO2. But other gases, of course, are greenhouse gases like methane, CH4, and nitrogen oxides, NO. Nuclear energy is the only large-scale, cost-effective energy source that can reduce its emissions while continuing to satisfy growing demand for power. So that is the situation of nuclear energy in our energy picture in general. I invite you to read the rest of the material that describes the need for nuclear energy. This is the two nuclear reactors that were being built in the United States. They are of the design that we call the pressurized water reactor. It has been licensed as an AP1000. 1000 stands for 1000 megawatts of capacity of electrical power, megawatt electric. AP stands for advanced passive. So this is the design that is much more advanced than the existing plants. And the two units here that when they started the construction, you could see the location of their, the foundation of their pressure vessels. Those units now are operating near Waynesboro in Georgia, Southern, a subsidiary of Georgia Power and Partners. But unfortunately, we don't have any nuclear power plants under construction in the United States at this time. You could see that it is a marvel in technology. Look how the pressure vessel just being, the bottom of the pressure vessel being downed in the Vogtle 3 unit. There are 4 units at that location. That's 900 tons, the bottom of the pressure vessel, and then the rest of the pressure vessel goes above it. So it's an amazing kind of technology. And the United States needs to regenerate back again its energy picture in general. This table here shows us the proposed United States electric generating plants by 2018. And but only the 2 Vogtle plants have been operating. The emphasis right now is on natural gas plants, 65 gigawatt electric, gigawatt electric, 67 natural gas plants, 21 wind farms, adding 22 of the capacity, and solar photovoltaics, 11 gigawatt electric, 11. So it's not, nuclear is not part of the picture yet. In the United States. This is the, of course, the unemployment rate in 2007, 2011, just before the energy crisis. The energy crisis destroyed capital with to a large degree. That's why the utilities have been reluctant to invest in nuclear power plants, which can cost up to the South Korean plants in the United Arab Emirates cost 5 billion a piece, 1,000 megawatt electric. In the United States, because of increased safety features, the utilities must come up to 8 to 9 kilowatt of $8 to $9 billion for a power plant. So in that case, the emphasis is only on small units. And one aspect of the technology is, of course, the introduction of robotics and artificial intelligence. This is a big buzzword today, where this is replacing human manufacturing and transportation jobs, and also robotizing education. Like here, we are using a Zoom connection instead of being in the same lecture room face to face. So in that case, society is going to be changing dramatically in our future. And in terms of the use of energy, this is our energy is our tool, or rather weapon, against poverty. And in that case, it's a human right for not just people in the United States and the industrialized nations, but the whole world to have a supply of electrical power and energy in general. Working in the energy field is rewarding from the perspective of contributing to the well-being of all of humanity. And I'll stop sharing here and maybe make sure that you go and look at our assignment for today. Turn in the assignment to Mr. Alvaro, and in that case, I will see if I can answer some of the. I cannot find my. This is the participants. By the way, the class can be dismissed now, but I want to find the chat room. I cannot find it. Chat room. Participants, yeah. Oh, here is a chat room. Thank you, Alvaro, for helping. If you have questions, I'll be available the rest of the afternoon if you have any questions.